Okay, so we're going to do some moments in equilibrium this time. So you've got loads of old exam questions and whatnot to practice these, but they are challenging questions. So I have a little process I follow for every question, and then hopefully I can solve it. So I do my sketch, and I draw on my forces, draw on the distances, because we're dealing with moments, and then take moments about a point. And again, I do anti-clockwise, take away the clockwise, and set that equal to 0. So you may need to do a combination of resolving and taking moments, or you may just need to take moments. It may be that if you've got two unknowns, you have to take moments about 2 different points. And to choose where to take moments about, you usually take them about a point where you've got lots of unknowns, or somewhere that's really convenient for the distances. Okay, then you'll have a set of equations and then you solve those. Forces you have to remember by yourself without being told in a question are weight, which we know is mg. Be very careful if you're given the weight, don't then multiply by g. Okay, occasionally we get bird's eye view situations, and if that's the case, then you don't need to worry about weight. Wherever you're in contact with your object and anything else, so it could be a rod, it could be the ground, it could be a wall, whatever it is, you need to have a normal contact force. Okay, so we usually call that one R. And it's always perpendicular to the surface you're in contact with. Perpendicular to that, you may also have friction. Okay, and that's if the question mentions rough surface or rough floor or whatever it is. So if you find the word rough in the question, you need to include friction. Friction does not have to equal mu r, it only equals mu r if you're moving or you're in limiting equilibrium or on the point of moving. Okay, otherwise friction is 0 up to that value. If you've got some string, then you have tension and that pulls away from the object. If you have a rod, you could also have thrust, which pushes into the object. Okay, so those are the ones you need to remember yourself. Often in a question, you might be given an angle, and it might be in the form like tan theta equals such and such. So if you know either sine, cosine or tangent, do a little right angle triangle, put on your, say, opposite and adjacent, and then work out using Pythagoras. Don't do sine of that angle, inverse sine, and then use your calculator with some horrible decimals. Right. If you've got more than one object in contact, you can either combine the two objects together as one giant object and ignore any forces between the two. So sometimes that makes life easier. Or if that's confusing, or if the question requires it, you can just draw your picture and then only draw the forces acting on one of those objects. Then separately do the same copy of the picture, but draw the forces only acting on the other object. And in that case, for those two separate objects, you may have contact forces between them. If they're attached with string, then it'll be tension. If not, it'll be normal contact forces and friction. Right, so we'll have a go at an example. This is a classic, our lovely ladder. So we have a uniform ladder. So if it's uniform, we know the weight's going to act in the middle. So let me draw the ladder first of all. So here's my ladder. Okay, and I'm going to have a floor and a wall. Okay, and I know that my ladder has got weight 150. Okay, that's acting in the middle. Okay, the total length is 4 meters, so I know that this length will be 2 meters. Okay, right. Rest in equilibrium, so it's not moving, with the end A in contact with a rough floor. So I've got a rough floor. If I've got a rough floor, I've got the word rough, I need to think about friction. So at this end that they're calling A, okay, we're going to have a normal contact force, okay, so I'm going to call that one RA, and we're going to also have friction. Now the ladder is going to feel like it's going to start sliding that way, so our friction is going to act opposite to that. Okay, and the end B is resting against a smooth, thank goodness for that, we don't need friction here, vertical wall. So we just need the contact force. We're going to call this point B. Whoops. So then that one is, I'll call this one RB. Right. The ladder is inclined at an angle of theta to the horizontal. So this angle is theta, okay, where tan theta is 3. So I'm just going to draw myself a little triangle separately for my theta. So here's theta. If we know tan theta is 3, that means it's opposite over adjacent. Opposite would be 3, adjacent would be 1, and if you square those and add them in square roots, you get 10, root 10. Okay, so that's going to be handy for finding sine and cosine of theta. Right, now, a man of weight 750 newtons is standing on the ladder at a distance x from A. Okay, so here we go. I'm going to put this man in red just to make it a bit easier to see. Let's have, here's our 750 newtons person, and this distance here is going to be x. Right, so we've got to the end of the paragraph. We've drawn our diagram, we've drawn on all the forces and distances, and we'll try not to get too confused by looking at it. It's quite tricky. First one, show the magnitude of the frictional force exerted by the ground on the ladder is given by that expression. Okay, so if we look at the diagram, then we can see that we're talking about this F here. So I want to find F. So if I think about things that are going to involve F, right, well, if I resolve horizontally, that's going to involve F. So let's do that first. Okay, so if we resolve horizontally, in that direction I've got F, and against it I've got RB, so minus RB, and that has to equal 0 because we're not moving anywhere. So that then tells me, that might be handy later, that RB and F are the same, they're equal. Okay, right, now it would make sense to take moments. So if we take moments about this point A, then we don't need to worry about these two forces because the distance to those is 0. So then I'm just going to have an equation involving numbers and RB. And when we know RB, we know F. So that's what we'll do. So, okay. So we're going to take moments about the point B, which is, A, which is at the bottom. All right. I'm going to start at, I'm going to start at the top end, okay. So I need to watch out for angles. I'm going to do the distance to my force RB, and I want the perpendicular component of that force. So I can see that using my alternate angles, Z angles, okay, then this angle is theta, so I would like the opposite side to that. So we have got, the distance is 4 meters times by RB sine theta. Okay, now if I put my pin in this end and we pull that way, we're going to make the ladder go anti-clockwise, so it's a positive value. Right, okay, now let's go along to 750 newtons. So this time, we're going to, if we pull that way, we're going to make the ladder go clockwise. So we're going to have a negative, and we want to do a bit of the 750 newtons. So let's think which bit. If we put in our little angle theta, just like when you're doing weight, okay, we can see that we need the cos part, the adjacent part. So we've got 750 cos theta, and we need to multiply by the distance, which is x. Okay, right, now we've got this force here, which is the weight. So this time we want the adjacent part. If we pull on this one, we're going to go clockwise. So we're doing negative 150 cos theta, okay, and we need to times by 2. Right, now if it's in equilibrium, all of those moments will add up to 0, okay? Because we don't need to include these because the distance is 0. We've done our other 3 forces. Okay, so isn't that pretty? So now we can substitute in our sine and cosine and do a bit of tidying up. Okay, so sine theta is going to be 3 over root 10. So we've got 4 times 3, I can do that, is 12. 12 over root 10, Okay, RB. Just scroll this down a bit so we can see it. Okay, and then we've got 750, and cos theta is going to be 1 over root 10. So minus 750x over root 10. Okay, and then we've got minus 300 times 1 over root 10. Okay, so I'm thinking I want to multiply 3 by root 10 there because it's awful. And so we then get 12RB. And I'm going to move the other bits to the other side, is equal to 750x plus 300. Okay. And if we then divide by 12, okay, we can simplify that out and get the original expression, which is 25 over, I'm trying to remember now, loop 2. Go back to where we were. So we had 25 over 2, 2 plus 5x. 25 over 2. So if I do 750 divided by 6 and then divide by 25 over 2, then I'm going to get 5x, and this will be 2. Okay, and that one's done, that part. Okay, we will